Download this code from codegive.com, link in the description below. Virtual machines, VMS, versus containers, a deep dive. This tutorial provides a comprehensive comparison of virtual machines, VMS, and containers, two popular virtualization technologies. We'll explore their architectures, advantages, disadvantages, and use cases, along with code examples to illustrate key differences. Understanding the core concepts. Before diving into the specifics, let's establish a clear understanding of what VMS and containers are meant to achieve. Goal Both VMS and containers aim to isolate applications and their dependencies from the underlying host system. This isolation provides benefits like resource isolation. Each application gets its own dedicated resources, CPU, memory, disk space, preventing interference between them. Security. A compromised application in one VM or container is less likely to impact other applications running on the same host. Portability. Applications can be easily moved between different environments, development, testing, production, without significant modifications. Consistency. Ensures applications behave the same way regardless of the underlying infrastructure. 2. Virtual machines, VMS. Architecture. A virtual machine, VM, is essentially a complete operating system, OS, running on virtualized hardware. This hardware is emulated by a software layer called a hypervisor. The hypervisor sits between the physical hardware and the VMS. Key components. Host machine. The physical server providing the resources. Hypervisor. The virtualization software, example VMware ES11, Microsoft Hyper-V, KVM. It manages the VMS and their access to the underlying hardware. Guest OS. The operating system running inside the VM, example Windows Server, Ubuntu Linux. Virtual hardware. The virtualized CPU, memory, disk, network interfaces presented to the guest OS. Applications. The software running within the guest OS. Two types of hypervisors. Type 1, bare metal, runs directly on the hardware, example VMware ES11, Microsoft Hyper-V Server. Offers better performance because it directly manages the hardware resources. Type 2, hosted, runs on top of an existing OS, example VMware Workstation, VirtualBox. Easier to set up but generally has lower performance due to the overhead of the host OS. Illustration. See code example, conceptual, VM creation using virt install with KVM. While we can't directly show code that emulates hardware, this example demonstrates how you might create a VM using virt install, a command line tool for creating VMS with KVM, kernel-based virtual machine, on a Linux host. Explanation. Virt install, the command to create a new VM. -name, specifies the name of the VM. -memory, allocates 2048 MB, 2 GB, of RAM to the VM. -vec+, assigns 2 virtual CPUs to the VM. -disk, creates a 20 GB disk image file for the VM. *-OS variant, specifies the OS type, Ubuntu 20.04. Helps with configuring optimal settings. *-location, provides the URL to the OS installation media. *-graphics VNC, configures the VM to be accessible through a VNC, virtual network computing, client. *-no auto console, suppresses automatic console connection. Important asterisk: this requires KVM and libvirt to be installed and configured on your Linux system. Disadvantages of VMS asterisk. Asterisk strong isolation asterisk VMS provide complete isolation between applications because each has its own OS kernel. This is crucial for security-sensitive workloads. Asterisk OS compatibility asterisk VMS can run different operating systems on the same host, enabling you to support legacy applications or applications requiring specific OS versions. Asterisk full control asterisk you have full control over the guest OS within a VM, including kernel-level modifications and configurations. Asterisk mature technology asterisk VMS have been around for a long time, so they have well-established tools and support. Disadvantages of VMS asterisk. Asterisk high resource overhead asterisk each VM requires a full copy of an OS, consuming significant disk space, memory, and CPU resources. Asterisk slower boot times asterisk starting a VM involves booting a complete OS, which takes considerably longer than starting a container. Asterisk larger image size asterisk VM images are typically large, several gigabytes, due to the included OS, making them less portable and requiring more storage. Asterisk licensing costs asterisk operating systems running within VMS might require licenses, adding to the overall cost. 3. Containers. A architecture asterisk. Asterisk containers are a form of OS-level virtualization. Instead of virtualizing the hardware, containers share the host OS kernel and isolate application processes using namespaces and control groups. Asterisk key components asterisk. Asterisk host machine asterisk the physical server running the container engine. Asterisk container engine asterisk the software that manages containers, example Docker, containered, CRIO. Asterisk container image asterisk a lightweight, self-contained package that contains the application, its dependencies, and configurations. Images are layered, using a copy-on-write mechanism to minimize storage. Asterisk application asterisk the software running inside the container. Asterisk libraries and dependencies asterisk the required runtime libraries and dependencies for the application. Asterisk namespaces asterisk isolate processes from each other by providing separate views of the system, including process IDs, PIDs, network interfaces, mount points, user IDs, etc. Asterisk groups. Control groups limit and account for the resources used by a group of processes, such as CPU, memory, and I/O. B illustration asterisk. See code example, Docker. Let's illustrate building and running a simple Python Hello World application in a Docker container. 1. Create a Python script, appy. This uses the Flask web framework to create a simple web application that returns Hello World from Docker. 2. Create a requirements.txt file ***. This lists the Python dependencies needed for our application, Flask. 3. Create a Docker file ***. Explanation of the Docker file *** from Python 3.9 Slim Buster, specifies the base image to use. This image provides a Python 3.9 runtime environment, Slim version for smaller size. *workdir/app, sets the working directory inside the container to /app. *copy requirements.txt, copies the requirements.txt file from the host to the /app directory inside the container. *run pip install, installs the Python packages listed in requirements.txt. -no cache dir avoids caching packages, reducing image size. *copy app.py, copies the appy file to the /app directory inside the container. Asterisk expose 5000, exposes port 5000 of the container to the outside world. This is where our Flask application will listen. Asterisk env name Docker, sets an environment variable name to the value Docker. This variable can be accessed from within the application. Asterisk cmd python, appy, specifies the command to run when the container starts running the Python application. 4. Build the Docker image asterisk asterisk. This command builds a Docker image named myPython app using the Docker file in the current directory. 5. Run the Docker container asterisk asterisk. Asterisk Docker run, runs a container from an image. Asterisk D, runs the container in detached mode, in the background. Asterisk P5000:5000, maps port 5000 on the host machine to port 5000 inside the container. This allows you to access the application from your host machine. Asterisk myPython app, the name of the image to run. 6. Access the application asterisk asterisk. Open your web browser and go to http://localhost 5000. You should see Hello, World from Docker. Advantages of containers asterisk. Asterisk lightweight asterisk containers share the host OS kernel, making them much smaller and faster to start than VMS. Asterisk faster boot times asterisk containers start almost instantly because they don't need to boot an entire OS. Asterisk higher density asterisk you can run many more containers on the same hardware compared to VMS, leading to better resource utilization. Asterisk improved portability asterisk container images are easily shared and deployed across different environments, development, testing, production, as long as the container engine is available. Asterisk DevOps friendly asterisk containers are central to DevOps practices like continuous integration / continuous deployment, CI/CD, due to their portability and reproducibility. Disadvantages of containers asterisk. Asterisk less isolation asterisk containers share the host OS kernel, which means they are not as isolated as VMS. A vulnerability in the kernel could potentially affect all containers on the same host. Asterisk OS limitations asterisk containers typically run applications designed for the same OS kernel as the host. Running applications with drastically different OS requirements can be challenging. Although technologies like Windows containers and tools for cross-platform containerization are evolving. Asterisk security concerns asterisk while container security has improved, sharing the kernel requires careful configuration and monitoring to prevent potential security breaches. Asterisk dependency on container engine asterisk containers rely on a container engine, like Docker, to run. Issues with the container engine can affect all containers. 4. VMS versus containers, a detailed comparison table. Feature virtual machines, VMS, containers. Virtualization level hardware OS, operating system. OS overhead high, full guest OS for each VM, low, shares host OS kernel. Image size large, GBS, small, MBs. Boot time slow, minutes, fast, seconds. Isolation strong, kernel level, weaker, process level, but improving. Density low, fewer VMS per host, high, more containers per host. Resource utilization lower higher. Portability moderate, requires hypervisor compatibility, excellent, portable container images. Security more secure, stronger isolation, less secure, kernel sharing, but improving. Use cases, running different OSes on the same hardware, microservices architecture. Testing incompatible software, continuous integration/continuous deployment. Legacy applications, web applications. High security requirements, rapid application development. Management more complex, managing VMS and guest OSes, simpler, managed by container orchestration. When to choose VMS versus containers. Choose VMS when you need strong isolation for security reasons. You need to run applications that require different operating systems. You need to support legacy applications that are not container friendly. You need full control over the OS and kernel. Choose containers when you need fast deployment and scalability. You want to maximize resource utilization. You're building microservices-based applications. You need portability across different environments. You're using DevOps practices like CI/CD. 6. Hybrid approach, VMS and containers working together. In many real-world scenarios, a hybrid approach is the best solution. You might use VMS to provide a basic level of isolation for different workloads, and then use containers within each VM to further isolate and manage individual applications. For example, you could run a Kubernetes cluster, which manages containers, within a set of VMS. 7. Conclusion. VMS and containers are powerful virtualization technologies with distinct characteristics. Choosing the right technology depends on your specific requirements, priorities, and the nature of your applications. Understanding the trade-offs between isolation, performance, resource utilization, and portability is crucial for making informed decisions. As container technology matures and security improves, containers are becoming increasingly popular for a wide range of applications, especially in cloud-native environments. However, VMS remain a vital technology for scenarios where strong isolation and OS compatibility are paramount.